Why hasn't NASA ever built a follow-up to Voyager? Hold on. Let's just sit with this question for a second, because this is exactly the kind of thing that keeps me witty. Hey, awake at 2 in the morning with my brain refusing to shut off. Read it again, slowly. Next year marks the 50th anniversary of Voyager's launch. Given everything that's changed technologically since 1977, why has a true successor never even been attempted? Something that could outperform Voyager 1 and Voyager 2 on every front, and do it in half the time while gathering far richer data. That question is fantastic. Genuinely, completely, outrageously fantastic. And here's why. On the surface, it sounds like a question from someone who doesn't understand how SPAS-E agencies operate. But actually, it's the opposite. It's the question of someone who understands the universe perfectly well, someone who raised their hand and said, hold on a second. We sent 2 incredible spacecraft out there half a century ago, running on what is basically Stone Age computing power. And now we have tools that would make a 1977 engineer's head spin. So why on earth haven't we already gone back out there with something better? And then a second question landed, even wilder, even more beautiful. Why has nobody ever tried sending a probe straight up and down through the solar system on a path perpendicular to the plane where all the planets orbit? Buckle in, because today we're going somewhere far, far out. Let's rewind for a moment, back to a warm Florida morning on August 20th, 1977. At Kennedy Space Center, a Titan IIIe Centaur rocket lifts off from Launch Complex 41, carrying a probe weighing just under 1,600 pounds. Its name is Voyager 2. 16 days later, on September 5th, its twin, Voyager 1, follows behind it, oddly numbered ahead of the craft that launched first, because its faster, more direct trajectory would get it to Jupiter and Saturn sooner. Now stop and really think about what technology looked like in 1977. The iPhone was still 3 decades away from existing. Personal computers were barely a concept most households had encountered. And the 2 most ambitious space probes humanity had ever built, machines designed to reach the outer edge of the solar system, were flying with onboard computers, holding roughly 69.63 kilobytes of memory. 69.63 kilobytes. Your smartphone right now holds memory roughly 1,000,000 times larger than that. 1,000,000 times. And we're not talking about something trivial like storing a text file. We're talking about the exact same onboard computers that navigated 2 spacecraft through the outer solar system, managed every system during close flybys of 4 giant planets, and are, right now nearly 50 years later, still executing commands and transmitting data back from interstellar space. Their radio transmitters broadcast at a power of just 23 watts, less power than an old incandescent light bulb, and with that almost laughably small amount of power, those signals cross billions of miles of empty space and still reach our antennas here on Earth. If that fact doesn't give you chills, I honestly don't know what will. Right now, at this exact moment, Voyager 1 sits roughly 15 billion miles from Earth. A radio signal sent from the spacecraft takes over 22 hours, traveling at the literal speed of light just to reach us. It remains the most distant human-made object anywhere in the known universe, and it's still functioning, still transmitting, still sending back genuinely valuable data 50 years after launch, powered by a computer with less memory than a modern digital greeting card. Every once in a while, human engineering absolutely nails it. Voyager 2 sits a bit closer, around 12.4 billion miles out, but it holds a distinction that no other spacecraft in history shares. It is the only probe ever to fly past all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune. The only one, period. To this day, nearly 50 years after that mission launch, no other spacecraft has ever reached Uranus or Neptune. Not a single one. Almost everything we know about those 2 ice giants comes from a brief flyby conducted by Voyager 2 using instruments that are now half a century old. Sit with that for a second. 2 entire planets in our own solar system have been visited exactly once, 50 years ago, by a spacecraft carrying less computing memory than a musical birthday card. So, of course, the question writes itself. Why hasn't anyone sent something better? Here's the answer, and it's the kind that disappoints almost everybody who hears it for the first time. But it happens to be completely true. The precise set of circumstances that made the Voyager missions possible in the first place were so rare, so specific, and so astronomically fortunate that they are essentially unrepeatable for roughly another 120 years. Yes, you read that correctly. 120 years. But let's not stop at the short answer, because what's actually underneath it is far more fascinating than a simple, it can't be done. The entire success of the Voyager program hinged on one single cosmically rare event, a grand alignment of the outer planets. In 1977, and only in that specific narrow window of time, the 4 giant planets of our solar system happened to line up in a configuration that allowed a single spacecraft to visit all 4 of them in sequence. Jupiter, then Saturn, then Uranus, then Neptune, one after another, almost like gates on a cosmic slalom course. Each planet's gravity used to accelerate and redirect the spacecraft toward the next stop. This technique is called a gravity assist, sometimes described as a gravitational slingshot, and it remains one of the most elegant ideas ever produced by space engineering. The concept itself is beautifully simple once you break it down. As a spacecraft approaches a planet, that planet's gravity pulls on it, accelerating and bending its path. If the trajectory is calculated with enough precision, the spacecraft leaves the encounter moving faster than it arrived, having effectively siphoned off a tiny amount of orbital energy from the planet itself. The planet slows down by an amount so infinitesimally small it's essentially unmeasurable, while the spacecraft gets flung outward like a stone launched from a slingshot. Without that rare grand alignment, this entire cascading technique, Jupiter feeding into Saturn, feeding into Uranus, feeding into Neptune, simply wouldn't have been possible. The planets wouldn't have been positioned correctly, and the sheer amount of fuel required to reach all 4 destinations without relying on gravity assists would have been so enormous that any such mission would be completely impractical with any reasonably sized spacecraft then or now. A young NASA scientist named Gary Flandreau deserves to have his name written in bold, permanent letters across the history of space exploration. In 1965, while working at the Jet Propulsion Laboratory in Pasadena, Flandreau was studying possible trajectories for missions to the outer planets when he noticed something extraordinary, something almost too good to be true. Toward the late 1970s, a planetary alignment would occur that was about as rare as these things get, an opportunity window that only opens roughly once every 175 years. The previous window had occurred back in 1801. The next one wouldn't arrive again until somewhere around the year 2150. Flandreau essentially told his colleagues, "We have about 12 years to design, build, and launch something to catch this window. After that, the opportunity closes and doesn't reopen for nearly 2 centuries." NASA listened. Congress opened up the funding. The Voyager spacecraft were designed, built, and launched right on schedule, and the rest became cosmic history. But that train has already left the station. The alignment window is closed, and every decade that passes from this point forward is another decade in which the outer planets drift further away from that once in 2 centuries configuration. We simply cannot repeat that particular trick. Not with the same elegance, not with the same efficiency, not with the same scope that made the original Voyager mission possible. And here's where the question really starts to bite. This is the part that genuinely deserves a serious, honest, enthusiastic answer. Has technology improved dramatically since 1977? Absolutely, yes, without question. Modern propulsion systems are vastly more efficient than anything available half a century ago. Scientific instruments, spectrometers, particle detectors, magnetometers, cameras now offer sensitivity and resolution that would have sounded like pure science fiction back in 1977. Communication technology has improved beyond comparison. Even the ability to process data directly on board a spacecraft, rather than transmitting every raw byte back to Earth for analysis, has changed dramatically over the decades. But, and this is a genuinely important but, there remains one physical limit that no amount of technological advancement can fully overcome, and that limit is distance. Distance is an absolute tyrant. Distance doesn't negotiate. Distance is completely unimpressed by how many transistors you can cram onto a modern microprocessor. Even with a rocket far more powerful than anything available in 1977, reaching the true edge of the solar system still takes decades, not years, decades. New Horizons, launched in 2006 on the fastest trajectory ever achieved by any spacecraft heading into the outer solar system, still took 9.5 years just to reach Pluto. 9.5 years. And Pluto sits relatively close to the inner edge of the Kuiper Belt, still enormously far from the heliopause, the boundary where the solar wind crashes into interstellar space, the same boundary Voyager 1 finally crossed back in 2012. Sure, New Horizons used a Jupiter gravity assist to gain significant speed along the way, but without that rare grand alignment of all 4 giant planets, you simply cannot chain together that same sequence of slingshots. You get Jupiter, maybe Saturn if you're lucky with timing, and then you're on your own, coasting through the void on whatever velocity you manage to build up. But here's where things get genuinely exciting. The part that actually makes my pulse quicken a little. There are serious, extraordinarily serious plans currently underway to send a modern spacecraft to the edge of the solar system within a realistic time frame. NASA and the Johns Hopkins Applied Physics Laboratory have spent years developing the concept for what's called an interstellar probe, a spacecraft purpose-built to push past the heliopause and study the interstellar medium with entirely new modern instruments. And the most ambitious version of this plan involves something genuinely audacious, using the sun itself as a gravitational slingshot. Here's how the idea works. You fly a probe dangerously close to our own star, closer than 10 solar radii, roughly 4.3 million miles from the sun's surface, a region where temperatures soar into the tens of thousands of degrees. And you use the sun's colossal gravity to fling the spacecraft out of the solar system at speeds that dwarf anything the Voyager probes ever achieved. This is known as the solar Oberth maneuver, named after the German physicist Hermann Oberth, who first laid out the theoretical basis for the technique. If engineers managed to pull this off, a probe using this maneuver could reach Voyager 1's current distance from the Sun in under 15 years, compared to the roughly 45 years it took Voyager to get there. 15 years, using modern instruments, so advanced they would likely bring the scientists who worked on the original Voyager missions to tears of joy. This isn't science fiction. This isn't a fantasy concept on a whiteboard somewhere. This is real, hard engineering, and hard engineering is precisely what humanity has always been good at when it puts its mind to it. Talking about a modern successor that follows in Voyager's footsteps along the same general path is already exciting on its own. But the second question that came in opens up a perspective so dizzying that I genuinely have to pause and take a breath every time I think about it. Why has nobody ever tried sending a probe straight up or down through the solar system on a trajectory perpendicular to the plane where all the planets orbit? Friends, this question is genius, and let me explain exactly why. To really understand it, you need to grasp something fundamental about the actual structure of our solar system. Picture the whole thing as an incredibly thin cosmic pancake. The Sun sits at the very center, and nearly every planet, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, orbits around it almost perfectly within the same flat plane. That plane is called the ecliptic, and it's a direct inheritance from the enormous cloud of gas and dust that the entire solar system formed out of roughly 4.6 billion years ago. When that massive cloud began collapsing and spinning, most of its material flattened out into a wide disk, exactly the way pizza dough spreads out thin and wide when you spin it in the air. The result is that nearly everything we know about the solar system sits within just a few degrees of this single flat plane. It's almost as though all the real action in the solar system takes place across one single horizontal surface, while above and below it, there's almost nothing there at all. Almost. And that's exactly what our question is really asking. What if we sent a probe to actually explore that almost nothing? What might we find above and below the ecliptic plane? Out at the same staggering distances where the Voyager probes revealed so many unexpected wonders along the flat plane? The honest answer, brace yourself, is that we simply don't know. We don't know precisely what's out there, and that gap in our understanding, that blind spot sitting right around our own cosmic neighborhood, might be the single most exciting thing I've come across all week. Now here comes the genuinely complicated part, though don't worry, it's complicated in a fascinating way. Sending a probe vertically relative to the ecliptic is technologically far harder than sending one that stays within the plane. The reason is brutally simple. Every single gravity assist we currently rely on, every planet we use to accelerate the spacecraft, sits within that same flat ecliptic plane. When we use Jupiter's gravity to give a probe a speed boost, that boost happens almost entirely within Jupiter's own orbital plane. To deflect a spacecraft significantly out of that plane instead requires dramatically more propulsive energy than staying within it. But, and this next but really matters, it isn't impossible. Both the European Space Agency and NASA have already pulled this off on a smaller scale before. The Ulysses probe, launched in 1990, was the first mission ever specifically designed to observe the Sun from polar latitudes rather than from within the flat ecliptic plane. To get there, it used a flyby of Jupiter, not to accelerate forward within the ecliptic plane like every other mission before it, but to be sharply deflected up and out toward the solar system's polar regions. Ulysses ended up in a highly inclined orbit around the Sun, which allowed it to eventually pass over both solar poles. The results were extraordinary. Ulysses showed us for the very first time how solar wind actually behaves at high latitudes, revealing that near the poles, it blows in a far more uniform and considerably faster stream than it does near the Sun's equator. It revealed the three-dimensional structure of the solar corona for the first time. It let scientists directly measure interstellar dust drifting into the solar system from outside. It uncovered aspects of the Sun's magnetic field that would have been completely invisible from an equatorial vantage point. But Ulysses stayed locked in orbit around the Sun the entire time. It never once headed outward into the deeper outer solar system. It never explored that enormous, largely unmapped region of space above and below the ecliptic plane that stretches out toward the Kuiper Belt and beyond. And that unexplored volume of space is exactly where this question wants to send a probe. Where I want to send a probe. Where honestly, all of us should want to send a probe. Now we enter genuinely wonderful territory, the border between science we already understand and science we're right on the edge of discovering. This is the territory of well-grounded speculation. the exact place where great scientists spend their careers, and where genuinely great discoveries tend to be born. The heliopause, that boundary where the solar wind finally gives way to true interstellar space, is not a perfect sphere. The Voyager missions only gave us solid data at 2 individual points along that entire structure, the spot where Voyager 1 crossed it, facing roughly the direction of the sun's motion through the galaxy, and the spot where Voyager 2 crossed it, in a somewhat different direction. 2 data points on a boundary that wraps entirely around the solar system in every possible direction. It's a bit like trying to understand the exact shape of a basketball by only touching it in 2 small spots. You'd get a rough general sense of it, but you'd miss an enormous amount of critical detail. From those 2 data points, combined with theoretical modeling, scientists believe the heliopause is likely asymmetric, more compressed on the side, facing directly into the interstellar headwind, and more stretched out and expanded on the opposite side. But what does it actually look like at high ecliptic latitudes, far above or below the flat plane where the planets orbit? We genuinely don't know. We have never sent a single spacecraft out there to check. And then there's the Oort cloud, that vast, mysterious, almost mythological spherical shell of comets believed to surround the entire solar system, the source of the long-period comets that swing through our inner solar system once every few thousand years, comets that have both terrified and fascinated human beings for millennia. The Oort cloud is thought to be distributed in a roughly spherical shape surrounding the solar system, not confined to the flat ecliptic plane at all. A probe deliberately aimed toward high latitudes could potentially pass directly through this region and finally give us precise, direct information about its actual structure and composition, rather than the indirect inferences we currently rely on. And beyond even that lies the interstellar medium itself, the material that genuinely fills the space between individual stars. Not a true, absolute emptiness, but a thin, diffuse mixture of particles, magnetic fields, and cosmic rays. At different latitudes relative to the ecliptic plane, the properties of that medium could differ meaningfully. Measuring those properties directly and comparing them against the existing Voyager data would finally give scientists a genuinely 3-dimensional picture of our solar system's true outer boundary. Not a single line, not a flat 2-dimensional map. An actual volume, a volume that no human eye, not even an electronic one, has ever laid eyes on before. So yes, the answer here is an absolute, unequivocal, enthusiastic yes. And this isn't just idle science fiction daydreaming. It's serious physics and serious engineering, actively being pursued by serious researchers inside serious laboratories with serious funding attached. Within the ongoing studies for the interstellar probe concept, researchers have already considered several possible trajectories, including a number that diverge significantly from the flat ecliptic plane. The overarching goal is to finally build the firsty, genuinely 3-dimensional map of the heliosphere, the enormous magnetic bubble generated by the solar wind that shields our entire solar system from the interstellar medium and, in a very real sense, makes life on Earth possible in the first place. And then there's the solar polar probe concept aimed at the outer solar system, an idea that's been circulating among planetary scientists with growing enthusiasm in recent years. The plan combines a dangerously close solar flyby with a trajectory that then rockets toward high latitudes well outside the ecliptic plane at tremendous velocity. A precisely timed close approach to the sun, paired with a powerful propulsive burn executed at exactly the right moment, using that same solar Oberth maneuver discussed earlier, could theoretically give a spacecraft enough acceleration to leave the solar system dramatically faster than any previous probe, and to do it heading in a direction absolutely nobody has ever explored before. The engineering challenges here are enormous, make no mistake. The heat shield required to survive a close pass just a few million miles from the sun's surface represents an engineering problem on par with what was already tackled by the Parker Solar Probe in recent years. And securing the long-term funding required for a mission like this demands exactly the kind of sustained, patient vision that has historically been the rarest resource in space policy anywhere in the world. But it is doable. It is physically, mechanically, scientifically doable right now with technology that already exists or is close to existing. The young scientists and engineers currently working on these interstellar probe concepts, on solar Oberth maneuver trajectory designs, on ambitious polar mission proposals, they carry the exact same intellectual bloodline as Gary Flandreau back in 1965. The same hunger, the same brilliance, the same fire burning behind their eyes. They're simply waiting for their moment to arrive. And I remain deeply, stubbornly, almost irrationally convinced that moment is coming, and probably sooner than most people expect. There's one more thing worth sitting with before we wrap this up, because it puts everything we've just talked about into perspective. The Voyager probes weren't just lucky in their timing, they were lucky in their design too. Engineers in the 1970s had no way of knowing their spacecraft would still be operational half a century later, so they built in redundancy after redundancy, backup systems layered on backup systems, simply because sending anything that far was already so expensive and so risky that failure wasn't an acceptable outcome. That same philosophy, over-engineer for the unknown, is exactly what future missions like the Interstellar Probe and any potential polar trajectory spacecraft would need to inherit. You don't get a second chance 15 years into a one-way trip toward the edge of the solar system. Every system has to work, every backup has to be ready, and every ounce of the spacecraft's mass has to justify its place on board. That's part of why these missions take so long to move from concept to launch. Pad, not because the physics is impossible, but because building something meant to survive decades in the coldest, most radiation-soaked environment humanity has ever tried to operate in, takes an enormous amount of careful, patient work. And maybe that's really the heart of the answer to the original question. It was never that nobody wanted a Voyager 3. It's that the universe only hands out that particular kind of gift once every couple of centuries, and everything since has required humanity to get clever in entirely new ways instead of simply repeating what worked before. The Obert maneuver, the polar trajectories, the interstellar probe concept, all of it exists precisely because engineers refused to just shrug and wait around for the next grand alignment in 2150. They looked at the problem sideways, found a different door, and started building the key for it. That's the story underneath the story here, and honestly, it might be even better than a straightforward sequel would have been. So, what do you think? Did any part of this raise new questions for you? Or maybe challenge something you assumed was true about why we haven't gone back? Honestly, it would be strange if it didn't. Drop your thoughts in the comments below. I genuinely read every single one. And if you want to go even deeper into this story, check out our full Voyager playlist, every video we've made covering the missions, their incredible journey, and the legacy they've left behind, all gathered in one place for you.